Hi there, Mr. Sutton bringing you a lesson on proving triangles similar. In this one, we'll be determining if two triangles are similar, and if so, why they are similar. For your warm-up, see if you can remember what the two conditions are for polygons to be similar. So this is just a review from the last lesson. There were two conditions, one of which was all the angles were congruent, and the other condition is your sides had to be in proportion. In other words, corresponding sides had to all have the same ratio. Can we prove polygons are similar with just one of these two things? How about if they all have the same angles? Turns out this is not enough. If you think about, for example, a square and a rectangle, those both have right angles, so the angles are all the same, but they are not always the same shape. And if you think about all sides being in proportion, is that enough? Well, that isn't going to do it either, because a square and a rhombus have proportional sides. I mean, all the sides in a square are the same, all the sides in a rhombus are the same, so they're going to be proportional, but they don't always have the same shape, the same angles. So you need both of these to prove most polygons are similar. Triangles, which we're going to focus on in this lesson, are a little bit different though. Triangles don't need as much to prove them similar. With a triangle, there's three ways to prove them similar. One is if you have two angles that are congruent. Another is if you have three sides, three corresponding sides that are in proportion with each other. Or another way to do it is if you have two sides that are proportional and congruent angles that are between those two sides. We'll take a look at each of these in turn. The first postulate we'll look at is the angle-angle similarity postulate, which says if two sets of corresponding angles in a triangle are congruent, then the triangles are similar. Now you might be wondering, well, wait a sec, don't you need all of the angles of a shape to be the same? Well, in a triangle, like these two triangles here, if you already know that you have two sets of congruent angles, then there's the same amount of degrees left over for the last angle, because triangles always have a fixed number of degrees in them, 180 degrees. So here we could say that PRB, triangle PRB, is similar to triangle WNM. And notice when I wrote my similarity statement that that's going in order of congruent angles. So P and W both have the same spot in the statement. Same thing with R and N, and also the leftover angles. So go ahead and pause the video and try this example out. Are these two triangles similar? And if they are, explain your reasoning. All right, let's see how you fared on this one. Now you might be saying, well, we have these right angles that are the same, but 26 and 64 are not the same angle, so maybe these aren't similar. Hold on just a second, though. What's the third angle in each of these triangles? Over here, it's going to be whatever 90 minus 26 is, because there's 90 degrees left over after using up this right angle. So that's going to be 64. And over here, there's 26 degrees left over. Oh, so we do have two angles, three angles really, that are the same. So we can say these are similar by AA. So one way to use AA that we just saw was by showing that angles are the same measure, the same number. Another way is with using some transversal relationships if you have triangles that are formed by parallel lines. So for example, check out these two triangles formed by parallel lines. We can show, for example, that angles A and D here are the same angle because with two parallel lines, these are corresponding angles. And we know that corresponding angles are congruent if you have parallel lines with a transversal. There's another pair of angles for the big and the small triangle in here that we can show is congruent. Angle C, right? It's the same angle for both triangles. We could call that the reflexive property when you have a shared angle between two triangles. Now let's look over at these two triangles formed by parallel lines. Looking at the parallel lines themselves, angles E and H, we know those are going to be congruent because those are alternate interior angles, and those are always congruent if your lines are parallel. By the same token, angles F and G are also alternate interior angles. And there's one other pair of angles that are going to be the same. These two J angles in here, angles EJF and HJG, those are going to be congruent because they are vertical angles. We're going to move on to talk about sides of triangles now. The side-side-side, or SSS theorem, similarity theorem, says if the ratios of three pairs of corresponding sides are equal, then the triangles are similar. So let's look at an example of this. We have these two triangles here. test to see if these are similar, we could set up proportions with all three corresponding sides. Now, which sides go with which? It sure looks like 6 and 4 go together, along with 9 and 6. However, maybe these triangles are facing different directions. To be on the safe side, the foolproof way of doing this is to realize that smaller sides of one triangle have to correspond to smaller sides of the other triangle. So, for example, the smallest side of the big triangle here, 3, has to go with the smallest side of the other triangle. There's no other way for it to be. So we can say 3 over 2, and then the next biggest side, 6 over 4, and then 9 over 6, the two big sides. Do those all reduce to the same thing? Well, 3 over 2 is fully reduced, 6 over 4 reduces to 3 over 2, and 9 over 6 reduces to 3 over 2. So we can say that yes, these triangles are similar by SSS. And to write the similarity statement, we can go PRB congruent, or not congruent, similar, just similar, to WNM. Here's another set of triangles whose sides are all given. Test these out and see if you can figure out if these are similar or not. All right, let's see how you did. So these triangles are not facing the same direction, so it would be a good idea to use that little trick I showed you on the last slide where we use the smaller side of one triangle and the smaller side of the other. So for example, 6 and 8 are going to have to go together. And then the next biggest sides, 9 and 10. And then finally the biggest sides of each triangle, 12 and 16. And what do these all reduce to? 6 over 8 reduces to 3/4. 9/10 can't be reduced. 12 over 16 reduces to 3/4. Unfortunately, these are not all exactly the same. Two sides are proportional, but not the third side. So we would say that this cannot be shown to be similar. The last one we'll look at is the side angle side, or SAS theorem, which says if the ratios of two pairs of corresponding sides are equal, and the angles between them are congruent, then the triangles are similar. So check out these two triangles. Here we see that W and P, those angles, are congruent. And if we check out the ratio of the sides that are the legs of those angles, so 24 over 40 and 27 over 45, again, smaller side over smaller side versus bigger side over bigger side, do these both reduce to the same thing? Well, this one reduces here to, let's see, these are both divisible by 8 actually, so this is 3/5, and this one is also going to be 3/5, reducing it by 9. Since we have angles congruent and their legs are in proportion, we would say that these are similar by SAS. And we could write our similarity statement, WNM similar to PRB. Pause the video now and see if you can prove that these two triangles are similar. All right, let's see how you did. I'm going to start by showing that these sides are proportional to each other. So we can say 9 over 15, and again I have to do smaller side over smaller side here, equals 18 over 30. Let's see if that's true. 9/15, that reduces to 3/5. 18 over 30, if you divide those by 6, that also reduces to 3/5. So we have two legs that are proportional. How about the angles between them? Well, this angle and this angle, those are vertical angles, so we know those are going to be congruent. So we can say, yes, these are similar by SAS. For the similarity statement, we have to be careful here. I'm going to say BEA is similar to BCD. Now, how do I know that E and C go together? Well, to get from B to E, I had to go along the shorter side, and that's the side that I'm going along when I go the other direction in this triangle. So that's it for proving triangles are similar. Until next time, this is Mr. Sutton signing off.